A venturimeter is shown below, which is fitted with a manometer. And the pipe has a cross-sectional area A1 at the inlet, and this converges to an area A2 at the constriction. Okay, so at point 1 you're going to have a cross-section A1, and at 2 you're going to have a cross-section A2. And assuming ideal fluid flow, we're asked to determine an expression for the flow rate in terms of the variables given below. So recall in ideal fluid flow, the flow rate is equal to the cross-sectional area by the speed of the flow, and that's constant. So effectively, we can either find A1 V1 or A2 V2. So that's the same thing. Now if we take two special points in the manometer, so remember that the fluid is going to exert a pressure such that the fluid is going to fill the manometer. And the pressure at A is equal to the pressure at C because the points are at the same height. So remember that the pressure is proportional to the height and the density of the fluid. So the pressure at point A is equal to the pressure at 1 plus the density of the fluid multiplied by gravity multiplied by the height, which is H1. Now the pressure at C is equal to the pressure at point 2 plus the density of the fluid multiplied by gravity multiplied by H2, and then plus the density of the fluid in the manometer. Okay, so that red fluid there has a density of rho m. We multiply by gravity by the height above point C, which gives us the pressure. And equating these two expressions, so therefore what we get is P1 plus rho F by G by H1 is equal to P2 plus rho F by G H2 plus rho M GH. And now if we subtract P2 from both sides, what we get is P1 minus P2, and then subtract rho F GH1 from both sides, well, what we get is rho F by G multiplied by H2 minus H1 plus rho M GH. And as we can see, H1 is equal to H2 plus H. So effectively, H2 minus H1 is negative H. So this can be written as rho F by G by minus H plus rho M GH. So therefore the pressure at 1 minus the pressure at 2 is equal to rho M minus rho F GH. Now using Bernoulli's equation, we can also get another equation. So what we have is P1 plus the kinetic energy at 1, so 1/2 by the density of the fluid, by the speed at 1 squared, and because both points are at the same elevation, we're just going to ignore the potential energy terms. Okay, so that would be equal to P2 plus the kinetic energy at point 2. And therefore, P1 minus P2 is equal to 1/2 by rho F. That's multiplied by the speed at 2 squared minus the speed at 1 squared. Okay, so remember that we're trying to find an expression for the flow rate. Now if we use the continuity equation, we can write one of these speeds in terms of the other. Okay, so I can write, for example, V2 is equal to A1 on A2 multiplied by V1. And if we square both sides, we get this expression, which we can substitute into here. Okay, so this gives me 1/2 by rho F, and that's multiplied by A1 on A2 squared multiplied by V1 squared minus V1 squared. So therefore, I'm going to get 1/2 by rho f by V1 squared, and that's multiplied by A1 on A2 squared minus 1. Because that's equal to P1 minus P2. And now we can equate these equations together. So that gives me 1/2 by rho f by V1 squared multiplied by A1 on A2 squared minus 1, which is equal to rho m minus rho f GH. And now doing a bit of algebra, well, if we multiply through by 2 and divide by rho f, well, that gives me rho m on rho f, and then rho f on rho f is simply 1. Then we can divide through by this term in the brackets, so that gives me V1 squared is equal to 2GH multiplied by the density of the fluid in the manometer on the density of the fluid in the pipe, and then minus 1, and that's divided by the ratio of the cross-sectional areas of the pipe squared minus 1. And now if we take the square root of both sides, well, what we get is V1 is the square root of this entire expression. And because we're asked to find the flow rate in the problem, so remember the flow rate is simply A1 by V1 or A2 by V2. So we just multiply this whole thing by A1, and that gives us our expression for the flow rate. Okay, so consistent with our problem, A1 is greater than A2, as we saw with this pipe over here. So the cross-sectional area of the constriction is smaller than that of the cross-section near the inlet of the pipe. And also the density of the fluid in the manometer is going to be greater than the density of the fluid in the pipe. And I encourage you to actually derive a similar expression for the flow rate using the cross-sectional area and the speed at point 2. And I'll see you in the next video.